in the week 10 of the course for the introduction to proteogenomics. So till week after looking at the individual uh, genomics and the proteomics technologies from the previous week, we had looked upon how we can integrate both the genomics and the proteomics technologies to look for a comprehensive image for the uh, disease or understanding the molecular basis of a particular disease. So now in this week we'll mostly be looking into a particular things like that, how we can select the best features or extract the best features out of it using different machine learning technologies. And in a later part we will be trying to look at the different pathways, understanding from the uh, differential expression of the genes of a particular disease condition. So what we are looking at here in the today we will be looking at, so since you know that if you use certain transcriptomics technologies or if you use proteomics technologies, then you will be getting a certain kinds of genes and their expression or your proteins and its particular expression. So now which features are able to differentiate when you try to predict that in the disease condition or in the normal condition, or if you try to predict in a way that if your that a drug is particularly acting on a particular person or not. So on the basis of all these things, if you want to do a prediction, so what analysis we are here looking at the prediction or the whether we are trying to predict, so which features would able to predict the different classes or different grades of your diseases, or which classes of the proteins would be able to predict your uh, different conditions of a particular thing. So here we are trying to do a prediction. So that's why the analysis is known as a predictive analysis. Now, a predictive analysis can be generally what we try to do is that we try to look at the different data sets with their different expression values. So if we have the data sets and different expression values, and then if we try to draw a boundary that which separates or segregates the two classes or the labels, class labels. So this boundary can be that it can be linearly separable as well as it can be it is non-linear, or it cannot be separable with a single line, drawing a separate single line. It need to it it is with any equation you cannot divide those two. And so this kind of, if you have to use this kind of boundary to separate the two classes, then it is called known as a not linear separable. That means that we need to have a higher polynomial order dimension to separate these kinds of data sets. So this kind of prediction, so mostly since we are talking about a predictive analysis. So if you remember in the week 5 we had extensively talked about the different non-supervised learning, like the clustering algorithms and all. But here what we are trying to do is that we have the different data sets, like 10 data sets, 20 data sets, 30 data sets, and now in the according to the two class levels or two class heads. And now what we are trying to do is that we are trying to separate both those data sets on the basis of a particular function, or classify those functions on those particular data sets. So now which comes under the level. So mostly we'll be talking about today is the supervised learning, or how the supervised learning on the models can be built, and the models can be optimized in a way that there is no cases of overfit or underfit, and helps us to segregate of the models in a better way. And it gives us an exactly way good separation or classification with higher accuracy, and with a very good sensitivity and specificity, which we'll be discussing today. So now if we are looking at the predictive analysis, so what are the questions that we are trying to answer using different omics data sets? So firstly is that to find out the markers to be using for differential diagnosis. So the markers which can, if we can segregate the things, and if there are certain diseases or certain markers that we can easily come ahead and separate that. Okay, so these markers are the ones that if we monitor these markers for a patient on a chipset or on a certain sets of chips, like you get in for the analysis for the rapid test and also a set of proteins if you monitor for a patient that he or she is going to the severity or those things, so then you can find out those markers using. So all these biomarkers and all those proteins that you have identified, like above 1,000 2,000 proteins, and from there you can try to find out those markers using the supervised and the unsupervised learning. So here, as I have already mentioned, that we will be using today, mostly discussing about the supervised learning, that we will be looking at the predictive analysis, which uses in the supervised way. In the supervised way, we know that we try to train our models with the different class levels that we define, and then we try to predict in the test data set. But here we'll be looking today mostly about that how the parameters can be optimized for the models, so that how the models can be fitted well without having a very underfit or a overfit data. So now the one thing for the two sets of thing, if we tell about, one is your classification and one is regression. So classification is just segregating a like binary. So if I give you an example of your classification and the regression, like a classic example is that whether today is if we are asked about your the weather, so whether it is rainy day or whether it is sunny day or not. So yes, so if you just segregate that these days are rainy day and these days are sunny day, so that kind of discrete classification is comes under your, so that kind of comes under your classification. But if regression is like kind of a continuous subset, where if that 6 days temperature, for example in a week you are recording 6 days temperature, after that what you are trying to do is that you are trying to uh, uh, form an line or fit a line or fit an, or come up with an equation, rather come up with an equation, so y equal to beta x plus something like that equation, and then you are trying to predict that on the seventh day what would be the temperature. So that is a classic example of a regression and the classification. So classification, what you are doing is that you are just classifying that what was the kind of your day, what was, it was rainy day, it was sunny day, it was whether it was there or not, just separating it, not doing anything else. Whereas in a regression, you are trying to predict the value of that, that in the seventh day, what would be the temperature on the basis of the 6 days temperature. So here in the case of proteomics datasets, what you can think of proteomics or genomics, like the transcriptomics datasets, what you can think of in the classification and regression is that classifying just in the method in the tumor control, severe, non-severe. Whereas in the regression, that when you have for a diseased person, particular gene X or gene Y or protein X or protein Y have these kind of expression values, then what can be the expression value for the n plus 1th person, that particular protein. So if you try to draw an equation out of it for a continuous variable and the data set, and then if you try to look at it and try to find out those particular values, so that comes under your regression. So this is are the two major differences between in the two major things that is generally performed under the supervised algorithms in the predictive analysis is the classification and the regression. So as I mentioned, that the classification is our label data where machine learning models get trained. So on the basis of the certain characteristics or the features, the machine learning model gets trained that okay, so this kind of expression level belongs, or this kind of patterns or characteristics belongs to this certain levels, and others belong to this certain levels. So what would be the output? So this comes under your label data with classes and the labels, and then finally your output has been done or is being provided. So this is the uh, classification model that generally takes place. So now, this is the major goal of the classification is to find out the prediction of the correct levels of a given input data. So now we need to predict that what would be the correct level for a given input data set. So if we get the correct level, so whenever we do classification, so our major goal is to that we can accurately classify into two levels or into the two levels what we are providing, and it gives accurate classification, so that one can know that whatever our goal is, if you are trying to help a surgeon or if you are trying to help a clinician, that whether this person has particular character, has particular severe or non-severe or something like that, and we're trying to predict. So we need to accurately classify. So there are different algorithms like your naive-Bayes, SVM, random forest, gradient boosting, logistic regression, etc. That gives you to perform the classification. That helps you in performing the classification. But the major goal is to accurately classify and which feature machine learning algorithm or which selection algorithm are used for this kind of classification. That becomes quite crucial to understand. So, for example, if all these algorithms are based, all these models are based on certain algorithms which tries to classify and tries to understand or capture. So we will be discussing how it is adjusted and all those. Then you will be able to understand that all these algorithms gives a certain weightage to different parameters, and the weightage is different, and that's why they behave differently. And then they predict in that some uses very complex things, some uses very simpler things. Also, in our data sets, the biological data sets, we need to understand that the number of samples generally remains very less, whereas the number of features becomes remains very much high, which leads to a problem and which leads to the uh, differences in your models being generally giving overfit or those things, and that we need to avoid. And that are many techniques which helps us in uh, avoiding and optimizing our parameters, that we will be looking into it. So here, after the classification model is done, so model you will be needing a kind of a training data set which will train your models on the basis of those levels, class levels, and then you will do a testing of your data sets to find out that what are the optimal parameters of the further testing. So this gives a confusion matrix where you have your true positives. So here, if for example, if you try to classify as with the classical example as I just mentioned, like the whether it is rainy or sunny day, anything, yes or no, if you take that on the basis by looking at the, so that you can do by looking at the temperature. Also, the what can be the features, if you think of that, if you are need to define that today's day was whether you should declare today rainy day or not. So what are the different parameters they would be looking on? The time through which the rain happened, the amount of rain happened in millimeter or centimeter, and how much is that is being affected, whether people are outside or inside. So all these are the features. So now you need to decide on that which feature. So generally what we are doing for all these features, so which feature will be deciding factor that whether it is rainy day or not. So most important feature would be the amount of rainfall and the time through which it happened, so that will decide upon. So uh, so on these things you need to train your model on the basis of that. So now if you give yes no, and on the basis of these features if you train the model and then you are testing it out. So now if you get that if it is rainy day and yes it is your rainy day, so these are known as your true positive. Similarly, if it is cancer and it has been predicted as cancer, then you will say that it is a true positive. Similarly, if it is not cancer and it has been predicted as in control, means it is not cancer, and it has been predicted as not cancer, then you will tell it as a true negatives. So similarly, if it is not cancer but it is predicting as cancer, or it was not rainy day but it is being predicted as rainy day, then you will tell it as uh, sorry, so if it is cancer and it is being predicted as not cancer, so if it is saying that whether the patient has cancer, but it is saying that the model is saying no, it has not cancer, or whether the patient is in the high grade status, but it is saying that it is no, not in the high grade status, so that is known as your false negative. Whereas if it is the other way around, that is a person is not cancer and is telling about the cancer, so this is the false positive. So these are the two types of errors. So in the proteomics studies, or these omics kind of studies, or in the transcriptomics kind of studies, we are we will be very much considerable about our false positives or the type 1 error. So just think what we are trying to do is that we have selected a list of biomarkers. For example, after you have performed the differential expression analysis, so you have got and identified a set of genes or the proteins showing variable expression. Now you have built a model and have gone to the clinics saying that this panel of markers, or this set of 10 markers, are able to distinguish very much the patients and can be used in clinics thoroughly. But what will happen, you just think what will happen, that if your model is that a person is having a cancer, and it is saying that it has no, that is the false negative, then you will be very much worried about your false negatives, because if you bring on or develop any kit, or do a set of kits, and if it gives you an erroneous result, like if it is a person having cancer and it is saying control, then that person will not get the treatment and it would cause an extremely difficult. So then you will be very much worried about this type 2 error. Whereas in the proteomics or the transcriptomics, if you do a statistical test and analysis, and you are saying that these biomarkers are very much important or responsible for your uh, very much coming very much differential in your analysis in whatever things you are analyzing, but you are finally getting that these biomarkers are not, so their false positives become very much crucial. But when you are doing a classification kind of test and you are taking it to the clinics and you are trying to find out the differences, then this kind of error, the type 2 error, becomes very much crucial. But whereas in the statistical test, and when you are proposing a certain biomarkers, a certain list of proteins or genes, then the type 1 error becomes, or the false positives becomes very much important. So this can be you can use interchangeably as well whenever, but the referring to false positives and false negatives. So whenever you refer to false positive, that is your type 1 error, whereas whenever you say to the false negative, so that is your type 2 error. So now there is a concept that how to train a model. So when we are saying that we are training the model or we are fitting into the data, but actually what is happening, or how the model is getting trained. So what parameters are deciding factors for the models to get trained or models to get better. So here, for example, see, it is a just a simple process as what we do in a regular classroom teaching. So, for example, teacher gives a lecture on it, a student tries to grasp, then a test is happening, and on the basis of the test, the teacher is giving him or her feedback, and again the student is learning. So, what we are trying to do here, we are trying to, so in a classroom, a student is trying to get the maximum number, and that is the reducing his or her error rate. And similarly, the teacher is on the basis of the feedback is providing the rules or the teachings, so that he or she can minimize his or her error rate. So here also the model, so as we are looking at the classification and looking at the accuracy, that how many true positive and the false true positive and true negatives are got identified. So here the model will be trying to classify it during the training, look at the test set parameter. If there is error, again it will give the feedback, and again it will train it, and again on the basis of that learning, and it will try to reduce your cost function, and on the basis how the cost functions are reduced, it will again try to optimize the model. So this is how it is performed, like the initial weight is given. So we will be discussing this in detail. So in key it will try to minimize the loss. So how the minimize the loss, I think you can understand that it is nothing but the local minima or the global minima. So if you do the partial derivative, and when it will be zero, so of the cost, then you will be getting the maximum zero error, and your maximum efficiency or the maximum accuracy of the class. So this is a general formula of how it is done. So here the method which is known as, or which is performed, is known as a gradient descent. So we will be looking at one of the methods that which helps us in having a better fit for the model. So as I mentioned that this classification on the machine learning model that we are doing, and if we are trying to fit into it, we would require the better classification model without underfit and overfit, specifically for our biological data sets. So now here what we are trying to do is that we are trying that how these models can be optimized in the best possible way. So for this reason, gradient descent is one kind of thing which helps us to uh, tune our models and build our models in such a way that it becomes robust and give provides accurate result. So what is gradient descent? So now we will be looking into it, that what is your gradient descent. So this is an optimization algorithm that is used to train machine learning models and your neural networks. So the both the ML models and the neural networks. So this is an known as your, in a better terms, is known as your optimization algorithm. So models learn by training data, and the cost function help to understanding its accuracy. So that's I mentioned that the cost function, or the cost or the error, that helps to that helps you to understand that how much accurate the model is. So until the function is zero, the cost function tends to zero or close to zero, the model will continue to adjust its parameters to yield your minimum possible error. So it's just a simple concept that whenever function till the time functions cost function is not zero, so it will have certain, it will possess certain kinds of error rate along with it. So what it is trying to do is that the function should tend to zero or close to zero, and this model will continue to adjust its parameters, and it will yield the minimum possible error. So gradient descent, what is happening that it is happening is to behave in a convex fashion. So you can see that it is behaving in a convex fashion, means the function that is being written, it should be in a convex fashion, and the steepness or the slope, whatever it is done when you are doing the derivative, your the in the initial stages the steepness will be high of the slope, and as you go on by increasing the weight and the incremental steps and the parameters, you will find, so you will find local minima at which step, and then finally ultimately we'll try to find the global minima. So this will help you to get that when the global minima tends to zero or close to zero, then what will happen is that you will get a minimum amount of error, and it will give the minimum possible error. So from the starting point, you use the derivative and use a tangent line to find the observe the steepness of your slope. So just think like that, if you in the weight and the cost function in the y-axis, if you just for any model, for any regression model or any kind of classification model, if you try to put into draw this curve, and then you are for performing the partial derivative at each point, and you are trying to find the local minima, and you are trying to increase or adjust the parameters, and as you are going on step by step, you are converging the error cost function towards zero with the partial derivative at zero, and then you are finally telling that it is giving the this particular point gives a minimal error. So the slope resembles your weight and biasness, and with the new parameters generated, the steepness will reduce, so until it converges to the lowest point of the curve. So this is your analysis for the predictive analysis. So what is the goal of the gradient descent? So we can easily understand now that the goal of the gradient descent is to nothing, is to minimize our error function. So whatever, whatever error function is there, we will need to minimize it. So here in the final, if you look at the final confusion matrix, whatever getting like the true prediction, yes, no, so all these things are calculated, like these error rates are calculated whenever you fit into a model. So in the model, in the backside, what happens is that during the training set, the algorithm performs all this to understand the cost function or derive the cost functions, and when the cost functions are derived, ultimately at the lowest possible function, it provides you the model, and then it performs on the test data and provides you the results. So it requires both direction and the learning rate. So you can understand that it requires both your direction and as well as your learning rate. So learning rate and the direction, what happens is that it determines the partial derivative calculations of next iterations. So so both your learning rate and direction is responsible for determining your partial derivative calculations of the next iterations to arrive at the local or the global minimum. So not only why directions are required. So if you can understand that if you are going in this direction, then only the partial derivative will come zero at the local minimum level, at or find the local minima that the partial derivative is coming lower than this point. Now if one is going in this direction, the learning the after learning and the error rate direction is going on to this direction, then what will happen is that the error or the this thing will come in a opposite direction, and it will find the local maxima, not the local minima. So if you go into the maxima stage, then it will not be helpful for you, because we need to find out the minimum error or minimum cost function. So that's why always the learning rate and direction is, both the things are important, and direction is very much important in understanding the finding the our minimum. So this is why both the things are equally responsible in your gradient descent. So now learning rate. So what is learning rate? If you try to understand now, so we have discussed that the gradient descent, any model, we need to find out the minimum function, so minimum cost function, and we need to find the maximal accuracy. So now the gradient descent or the learning rate, what is there is that the size of the steps undertaken to reach the minimum. So for instance, if you start from here, so if you take only one step, and you can come here directly, or you can take multiple steps in between to come here. So this is what is known as your learning rate. Now you need to understand that what kind of learning rate would you keep. Would you keep a very high learning rate or a very small learning rate, and try to find out the best minimum. So size of the steps undertaken to reach the minimum. So a small value evaluated and updated. So what is our learning steps by definition? So I'm hopeful that you have understood that how it is coming in the means how the learning steps are coming, what the incremental step while coming down the weights of this particular slope. So now if I say that the size of the steps undertaken to reach the minimum, so it is as nothing but a small value that evaluated and updated based on the behavior of the cost function. So whenever the cost function is undertaken and taken, so what are the that small value is evaluated after each and every step and tries to find out the new minimum or global minimum. So now the question is that whether you would be keeping a high learning rate that it will go directly to nearer minimum, or you will be going to for a low learning rate. So what is the differences between a small learning rate and a large learning rate? So you can see this is a small learning rate and a large learning rate. So this is the loss and this is the value of the weights. So for the small learning rate, you are going here. So here you will be finding the global minima. Here you will be finding. Here you will be finding. And the large rates you will find here, go here, here. So what happens is that a low learning rate you can understand from a simple view that each small weight is go on, its value is evaluated every time a small step is taken, the derivative is calculated and the partial derivative is calculated, global minimum is found out, then it is taken forward. So this you can understand easily that all these things are taken, small steps are being taken. So here you can easily say that the number of computations and the iterations and the computation time that will be taken will be huge. So there will be there is no doubt in that uh, it will be huge. But what happens if you take the large learning rate? Then when the computation times are increasing and all those complexities will increase, then what one would do, one would generally go for larger learning rate. But the larger learning rate, the problem is that you may miss out your your actual minimum. For example, here you have taken a step, here you have taken, here you have taken. Now if you go, this is the place. Okay, so minimum place would be this one, but the learning rate what which is being kept here, so it is getting the minimum here. So for a small learning rate, you are getting the minimum point here, and for a large learning rate, you are finding the minimum point here. So here you can understand that the cost function, it will have some error. It will definitely contain some error. That's why we have said that the direction and the learning rate are two of those things are very crucial in understanding that in finding the best model, best predictive model, so that the cost becomes function becomes minimum. So whenever so since you are trying to cut off or trade off between your computational time, and when you are saying that the learning rate and the learning rate is taking a huge time because it is taking small steps and it is coming so it is coming like this. So it is increasing your computational time, no question on that. But you are getting the best possible result. But when you are increasing your learning rate, that it is taking certain time and it is not coming so frequently good, so it's just increasing and finally you are losing at the minimum point and error. So we need to optimize in a certain way that the computational time also remains, as well as it the point at which the learning rate curve happens is also gets reduced. Yeah, so this is so we need to have an optimal landing rate so that we don't miss out the actual minimum and the cost function doesn't contain much error, as well as we need to look after the computation time. So predictive so another thing is our cost or loss function. So we are talking about the cost or loss function from a long time, but what is this actual cost or loss function? So this is nothing but it measures the difference or error between your actual and the predicted. So what is your actual value and predicted? So I hope you are understood. So in the models, whenever the model training is done, so it is always predicted that okay, so during the training that how much it is showing the error and the actual and the predicted ones. So it improves the model's efficiency. So how it is proving the cost of the loss function is improving your model's efficiency. So it is providing the feedback to the model so that it can adjust the parameters to minimize the error and find the local or the global minimum. So I am hopeful that you have understood as of by now. So at cost function, which is whichever is converging to zero, so model will stop learning. So now this is another important thing. So here whenever we had discussed that the your learning rate and the direction as we mentioned, right? So now in the learning rate and the direction, another major problem is that if we have chosen a very high learning rate, so then what will happen is that if the model reaches here, and since the rate is very high, it is coming falling below your it is not coming in the slope and the partial derivative cannot be constructed, then it will assume it as only the minimum of all those things, and it will model will stop learning. So that's why it is a problem. Whereas here the problem is that it in the each and every small step when you find out the error, it will give you the some kind of functionalities, and it will give you the feedback, and it will be updated, and it will be continued the learning. So this is the problem. So cost or loss function is mostly the same, but there is a subtle difference between cost function and loss function. So if you come across the term of cost function, so you will understood that it is also your loss function. But if you come across the term, so you need to understand there is a subtle difference between your cost function and the loss function. So loss function refers to the error of one training example, whereas cost function refers to the average error across an entire training set. So one training example like this. So here, if you the error rate is calculated, so then it is called as your loss function. But if it is across the entire data sets, this many loss functions are calculated like loss 1, loss 2, loss 3, loss 4, loss 5, loss 6. All these things, if all those things are calculated and averaged, then that is called your uh, cost function. But if it is for a single error of one training example, then it is called as your loss function. So whenever you come across these two terms, loss function and cost function, so you try to understand that the this is the error rate or the difference between your actual and the predicted ones. But the subtle difference is that one is that average of an entire data set. Another thing is that a single functional difference for each data set. So these are the two things which are the major differences for your loss function and cost function. So now in the gradient descent, so on which we are trying to optimize our models for the best fit, so to accurately classify our omics data sets. So what are the types of gradient descent that you can use? So one type is known as your batch gradient descent. So what is batch gradient descent? It is sums the error for each point updating the model only after all training examples have been evaluated. Okay, so what is batch gradient descent? So if from this example, if we try to understand, so it will sum up all those errors. So you can see that it is that sums the error for each point in a training data set, and it will update the model only after the training examples have been completed. So it will update only when the training example has been completed, and then again go back and try to uh, uh, find out the cost function or loss function. So this problem with the batch gradient descent is that have a long processing time for large training data sets, as it needs to store all of the data into memory. So it whenever it is calculating the cost function and is trying to find out, so it is having a huge you can understand the processing time will be huge. Secondly is that the memory time that it will need to store all of those data for those training data sets that which is coming uh, across the and then finally it will be able to store all of those data into memory. So convergent point sometimes doesn't becomes the ideal one in the case of your batch gradient descent. Sometimes the point that you get is doesn't, it is in the ideal one. Another type of gradient descent is the stochastic gradient descent. So I mean among the gradient descent, so the different types. One is your batch gradient descent, so which sums up the points of all those, and after the training example has been completed, it will give you the feedback and it will try to change the loop. But the problem that is there with this kind of approach is that you need to go well beyond the thing that that it takes a lot of memory and a lot of time. So in the stochastic gradient descent is that it updates each training examples parameter one at a time. So it will update your each training examples parameters one after time. So one it is being done examples parameters one, and it will update you. So easier to store in memories in once only one example to all data. So you can understand that it is uh, very much easy to store in memory. So frequent updates result in your noisy gradients. So helpful in escaping the local minimum and the finding the global one. So it is helpful which in finding the global minimum in the stochastic gradient descent. So one gradient descent is your batch gradient descent. Another one is the stochastic. Batch is that all the training examples, and then it will finally update it, and then finally you will be getting the minimum. But here you can do that after each training examples parameters one at a time. You can try to find out. So it is also easier to store in memory and find the global minimum. So now another kind of thing is that, so again you need to find a trade-off between that the best ideal one and the one which can be used for your practical analysis, like the learning rate and the if you decide the size and the steps of the learning rate. So this is a mini batch gradient descent which combines concepts from both gradient descent and your stochastic gradient descent. So stochastic gradient descent, like it updates after each once and easier to hold in memory. So this what it does is that it splits your training set, so it doesn't go for all the examples of the training examples like it what it happens in the batch set. Like it will go for 10 examples, 10 perform all those on the basis of the learning set, and then it will finally evaluate and then update it are the stochastic ones that with each example it is giving. So it is not the case. But here what it does is that it splits the training set onto small batches and perform the updates. So it will split your training set onto small batches, different batches, and then it will perform your updates. So it's the strikes a balance between the computational efficiency of batch gradient descent and the speed of stochastic gradient descent. So stochastic gradient descent is the very much speed requires speed, but it But the problem is that since it is updating after every training example. So for example, you are training A, training B, you are performing. So there are, for example, n number of samples. So n training set contains n number of samples. So after each and every one sample, you are updating it. So stochastic uh, gradient is what you say, that it is not so much computational efficient, but batch gradient is somewhat compared to the it is kind of because it is performing all the training set and then it is updating it, so kind of a computational efficient, but uh, it takes a lot of memory in that case. So mini batch gradient descent, what it does is that it splits your training set into small batches and then performs your updates. So now there are certain challenges that are associated with gradient descent. So we know that we are trying to find the model and we are trying to optimizing it in a best possible way, and that's why we are thinking of having a one kind of thing, that is the gradient descent. So that will help us in somewhat having a better model or the better accuracy by minimizing cost function, so having a different learning rates and your directions. But what happens is that there is a challenge associated with gradient descent. One of those is the known as the problem of the local minima and the saddle points. Okay, so the local minima and saddle point is one kind of a problem. So one problem is that it also struggles to find the global minimum for non-convex problems. So if the problems are convex like this, so if you have, so if I just show you like this, has no problem. So no convex, only one, it's the minimum, global minimum. But whenever the data sets become like this, where you have this also as a zero, this also as a zero, or so problem of the local minimum. So this is a problem which is defining your local minimum problem, where you have local minimum here as well, here as well, and then you have your saddle points. So here it is not the approximate error, means optimized function, but here there are the points. So what is happening is that difficult to analyze saddle points as cost function. So this kind of points, it is because very difficult to analyze these points as their cost function, because increases on one side and decreases on the other. So here in so whenever you are moving ahead, so it becomes a kind of an unidirectional, whereas in those cases, so where is in those cases, so if you go on one side it will increase and the other side it is going to decrease, so you are finding it. But here in this kind of saddle points, it becomes pretty difficult to understand that what is the local minimum or the global minimum to reduce the error. So this kind of cost function, it becomes crucial and it is not able to let you go beyond. So this is the major challenge with the gradient descent. So gradient descent has been helping to understand or evaluate your models constantly and to find out the minimal cost function. But when your data set or the data points becomes non-convex and there are two group minimas like these functions, the local minimum which tends to like be a global minimum at the saddle points, so then it doesn't work, or it cannot be, it becomes difficult to work with the gradient descent. Okay, so this was all about the gradient descent. So if anyone has any question. No, right? Okay, so then we will move on to the next topic. Or the next topic is known as your regularization. So here, so as I as I mentioned, that the major task is of the classification and then building the model and testing out its accuracy. So one way of looking at the cost function and the loss function and minimizing it is a gradient descent. But there is some difficulties with the gradient descent, and also the dimensions and the number of data sets and all those things also plays a role. So now what we are looking at the another concept of the regularization. So what is regularization? So this is another approach. So like the gradient descent, so regularization is also another approach that is used to calibrate machine learning models in order to minimize the adjusted long loss function and prevent your overfitting. So here you can see, so the major thing that we tend to look whenever we are developing any machine learning model and trying to test it out on our data sets, we tend to find out that both that it is not underfitting as well as it is not overfitting the data. So that's what it becomes very much uh, important. So here you can see that this model is overfitting, and in this in these data sets, the equation that has been taken is being overfitted. So a regularization, which is a kind of a calibration method. So I am hopeful that you all perform calibration in various things like your pH meter calibration and all those things you perform. So similar way is that used to calibrate these machine learning models in order to minimize your adjusted loss function and prevent this overfitting. So after regularization, you can see that this is the best possible fit that is being coming up after regularization. Otherwise, without using a regularization, your model was going to solve or get into connecting all those data sets and the data points. But after regularization, you can get a good fit over here, which is trying to separate your two classes or classify eight classes. So regularization, what it does, it helps the fitting your machine learning models appropriately on a given test set and hence reduce the errors associated with it. So all the errors that are associated with on a given test set, so it helps you fitting the machine learning models and hence reduce the errors that is being associated with it. So now what are the two types regularization techniques? So I'll just reiterate it once for all of you. So this firstly in the gradient descent, what we look upon is that to find out the cost function and reduce the minimize the cost function, and for that it required your learning rate and directionality, and that thing so we need to optimize what is should be the learning rate so that computational power and the efficiency both remains intact. Third thing, there were the three types of gradient descent: batch gradient descent, stochastic gradient descent, and your mini batch gradient descent, where you were combined both batch wise and the concept of batch and the stochastic, and it divided into sub branches and then taken forward. So this was mostly the thing. So now another thing concept what we are discussing right now is the regularization technique that helps to calibrate your machine learning models to get a best fit over the curve, and doesn't helps in doesn't let the model to go into a overfit or an underfit stage. So here the regularization that techniques are there. There are two types. One is a reach regularization or lasso regularization. Also in different literature and different things, you can also find out the names like the L1 and L2 regularization. So don't worry about that name. So the concept here, like so some literature will say you about reach regularization and lasso regularization, whereas some will tell you about your L1 regularization and the L2 regularization. So this is a very in the case of whatever we have seen as of now for biological data set or the kind of omics data sets where the dimensions of the data are huge and where the number of samples becomes very less. So this kind of regularization helps us to balance out the effect and reduce the error associated with any machine learning models and helps to predict it better. There is no doubt on that. So what is there? One is the bridge regularization. So it modifies the overfitted or underfitted models by adding your penalty equivalent to the sum of the squares of the magnitude of coefficients. So here there are major difference between your ridge regularization and lasso regularization is that in the ridge regularization, what it does is that it modifies by taking the sum of the squares of the magnitude coefficient of the errors. So for example, you have used this line to classify these data sets. Now, the more the data point is away from your this line or this feed that you have taken, so it is having that error. So how it will modify the ridge regularization will modify. So it will modify the model. So here, if you say that this is an underfit model because it is not able to segregate it very much. So in one side there are many data sets, and in one side very less data sets. uh, if it is for example take it different levels with equal number of data sets, so then this is not a kind of a good fit. So here what will do is that it's a penalty equivalent to the sum of the squares of the magnitude of the coefficients. So here you can see that the cost function will be loss plus lambda is equal to penalty for the errors. So how much penalty that you are giving for each error, so that will depend upon it. Then slope of the curve or line. So you will calculating here the slope or the error for each curve or each data point, and then you will be determining the coefficient or the cost function. So that is your ridge regularization, which will give you loss plus lambda into summation of the w square or the error square. So how ridge regression works? So for example, you have taken a linear regression line. So this is an example. So that how you will be calculating and how you will be getting a best fit, or it will help you in reducing the error, and it will help you to balance out the model in the error. So that's what regularization, that to calibrate the machine learning model. So you can understand now that why the calibrate word was used. So you can see that it is a kind of calibrating where you try to find out the with the, for example, when you try to calibrate your pH meter, you are trying to give the known pH solutions, and then trying to find out that what is the error rate, and then try to calibrate it that no, it is this much. So here also the principle and the concept is same, where you are trying to uh, calibrate this model. So here, for example, you take this linear regression line and it is coming as 1.96. So now if you are giving the penalty for this error 1 and the w error rate is coming zero point 0.7, then what is coming is your cost function, and this will give you the new line, or what you are calling as the ridge regression line. So this is known as your ridge regression line, which is you are forming. So now one is your linear regression line and another is your ridge regression line. So now you can see that the ridge regression line is able to classify in a better way than whatever linear regression line that was taken. So this is how it is performing. Okay, so I'm hopeful I'm clear. If anyone has any question, can do so. Okay, so that was about the reach regularization. So regularization. So after gradient descent, we are looking at regularization, and then we are looking at the we have looked upon the reach regularization. So now what we are looking at the lasso regression. So this, what is the major difference between the ridge regression and the lasso regression is that the ridge regression is modified by taking the squares, by summing up the squares of the penalty, whereas lasso regression modifies the overfitted or underfitted models by adding the penalty equivalent to the sum of the absolute values of coefficients, whereas one uses the square of the coefficients of the error rates and another is using the sum. It is not taking the square. So it takes the true values of the coefficients. So the function or the cost function is similar. So that's why it's important to understand the difference between whatever remains in your loss function and cost function. So loss function is at one example, at one particular training example, but in the cost function it is an over the entire data set. So if you take the loss plus lambda into summation of the w, so it takes the true values of the coefficients. So loss equal to sum of the squared residuals and w equal to the slope of the curve or line. So you can see that if you take, considering the 2 points on the line, so here uh, I don't know if you have noticed that the loss we are taking as 0. Why? Because the line that has been taken. So if you have the question in your mind, so why we are taking the loss equal to if the line is the through which the line is drawn or the regression line is drawn, and if it the process through the data sets process over the lines, then the loss is 0. So then what we are doing is that penalty equal to 1 and the cost function is 1.4. So this denotes your cost function. Similarly here, sorry, just yeah. So here it was defining your cost function. So here what you are getting that it is not doing the square. So you can see that it is taking just the absolute value and it is not doing the square. Then it is uh, performing the thing. So in this way it has got 1.4. So after calculating here, it has got the 0.8. So this is so one will take the squares of the weights of the coefficients and one will be the sum of the absolute values of the coefficients. So here is the major difference. One taking the sum of the absolute values of the coefficients, whereas one is taking the sum of the squares of the magnitude of the coefficients. So this is the major difference between your ridge regression and your lasso regression or the regularization. So any question up to that? So now we are clear about the models and that's why we are going for the gradient descent and regularization, which is trying to trade off between the models, machine learning models and the associated and the errors that is being associated with it. And then what we are trying to do is that we are trying to minimize. So if I just do a revision of it, so is that we are looking at the gradient descent. So this is nothing, this all are nothing. That is an optimization algorithm that is being used to train the machine learning models and the neural network. So it is goal is the gradient descent is to minimize the error function, which and the learning rate and the direction is quite important to calculate your partial derivative for understanding the global minimum. So then it will go to the size of the steps and how much. So it might be if you take a much larger size of the step, it may overcome or it may go out of the global minimum. And if you take smaller steps, it will take increase the computational time. So this is the definition of your cost function or the loss function. And then you try to do its batch gradient descent, and then you have the stochastic gradient descent, at which batch gradient descent that you will be updating after completing all the training examples, whereas for the stochastic gradient you will update after each training examples parameters one at a time. Then you have the mini batch gradient descent. Then there are the challenges with the gradient descent. So why this regularization or other methods are being into place, because of this kind of, whenever you have a non-convex problems, you have the problem of the local minimum as well as you have the saddle point through after which it is becomes difficult for you to calculate the global derivative and the minimum function partial derivative and the global minimum. So this is the another technique, that is the regularization, which is used for calibrating machine learning models. So adjusted loss function and prevent your overfitting. So that can be your reach regularization or the lasso regularization, whereas the reach regularization helps you to the adding the penalty equivalent to the sum of the squares of the magnitude of coefficients, whereas in the lasso regularization it helps you to it just takes you the weights of the absolute values of the weights and gives you try to a better fit of the model. So this has been example has been given taking the simple linear regression. So I am hoping that there is no doubt. So this is what we have discussed. So these are the algorithms like naive-Bayes, SVM, support vector machine, random forest, gradient boosting, logistic regression, etc., which are giving us the errors and which we are trying to minimize while training the models on the basis of using regularization or the gradient descent. So now in this, why we need to, once our model has been developed and the is being generated, so we need to have go through certain definitions to understand that how based or robust our models are. So in the case of if I just tend to you bring in terms of biomarker discoveries. So once you do a global data sets and analyze your data sets, and then when you finally go ahead and print and try to find out the biomarkers, then you will be performing or validating in a larger cohort of samples, followed by you will be doing in a blinded validation or test validation, where you will be a different population and different race, and you don't know exactly that how much it is separating or segregating, and you will be trying to find out those particular differences, those particular accuracies. But how you will be calculating the that how much accurate your model is, or how much accurate your set of proteins or genes markers that you are claiming is. So that's where comes the role of the different parameters that you will be checking or you will be calculating after your models is generated. One is your like your accuracy, which correct prediction of all the ones, so that you can understand from this only that true positives and the true negatives. So these are the two things that you are looking for your model to predict correctly and accurately. So the number of true positives and the true negatives divided by your total number of observations will be giving your accuracy. But this is not the only parameter, the how accurate your classification has become, or uh, how best is your classification. So this is not only the parameters, but there are other parameters also which you will be looking. So as I mentioned that you will be worried more about the type 2 error or the type 1 errors when you will be worried about what kind of errors. So one is the precision. So out of all the predictions, how many of are correct? So that out of all your predictions means that you will be comparing about the positives. So if you whenever just try to understand that whenever the terms, so this will become very much easy for you to recall whenever you perform anything or anything. Whenever you do this kind of analysis, if you do this kind of analysis, it will be becoming very much, or if you get this kind of data, it will be become very much easy for you to understand that how better or good your particular model is. So precision gives that out of all the predictions, how many are correct, means that it will include your both true positive or false positive. Why true positive as well as the false positive will be included here? So it is telling that how many are correct predicted. So whenever it is predicting that it is a positive, so if, for example, if you are doing a test for the severity of the patient, that it is telling that it is severe, 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 that means it is predicting. So it is predicting your model to be severe. So now that can be your true positive as well as some of the false positives. That is, the non-severe patients have also been classified as the severe patients on the basis of the data by your model. So then what will happen is that you are then what you are telling is that uh, so what you are telling is that uh, it is showing you the both false positive as well as your true positive. But what is happening here is that so what you are trying to do is that to match both the true positive and the false positives. So that's why you are trying to predict that how many among those predictions, both the true positives and the false positives, uh, how many are correct. So that gives you the precision. So precision is always among the positives. So both true positives and false positives will be in the denominator, and how many are correct, predictably correct. So now you need to understand. So as I have already said that your type 2 error and the significance of the type 1 error. And so now you will be understanding that only accuracy, if some things accuracy is not so great or not so high. So whether there are other parameters or other things through which we can try to understand that whether we can take it forward or not. So one major thing is the precision. So in that, so you know that so you need to now judge and weigh out that which having an how much if the precision is high or the sensitivity is high or the specificity is high, whether you can take that model forward or the whether the set of biomarkers forward or not. So that's why I have given you stressed out on the facts that which errors to be taken into effect or taken into mind whenever we perform any kind of this kind of analysis. So this is the precision. Now the concept of the sensitivity. How good was model at predicting real yes events? So real yes events means again true positive. So real yes events, this term only is saying that it was positive. So it will in the denominator. Now you can understand that what it will be having in the denominator is the for true positive as well as the false negative. So why false negative? Because that was actually true positive, that the patient was severe, but in a model in a negative way, what it happened, what it did is that it has given you the predicted that it is a negative, it is a non-severe. So how predicting real yes events? So how many true positives have been given under true positives and false negatives? And specificity gives you that how many was good at predicting your real no events. That is the true negatives among the true negatives plus the false positives. So it will just the other way around. So how many are predicting good at real yes events, good at real no events, and out of all predictions how many of are correct. So that will give you the precision. So whenever you will try to calculate your precision, so if that the out of all the predictions how many are your true predictions or the correct predictions. So the true positives among the true positives and the false positives. But the sensitivity would be your how good was your model at predicting your real yes events, that is true positives out of the true positives plus the false negatives which was mislabeled in the negatives. So similarly in the real no events it will be true negative plus false negative plus true negatives. So this is what the sensitivity is, specificity is, precision is, and accuracy is. So I am hopeful that it is clear to everyone, and you would be able to judge on the basis of that which kind of weights or the errors you are looking upon. So there is the things is that there are now I'll be focusing on these things. So since we are talking about the errors and those things, so now another problem is that there is two kinds of error. One is your training error and one is your testing error. Okay, so now why it is important to understand the concept. So for example, here you can see specifically in the neural networks or in the different algorithms when you use. So error rate starts here, and you are training your model and testing your model. So you can see that the error is decreasing. So at a certain point or a certain stage, okay, so the training has still some error, and if you go on training your model, but it at after certain points in your test set, again the error will go on increasing in the testing. So this is called, so here you have the increasing bias left side to it, and here you will have the increasing variance. So you need to stop your training here at this certain point, so that you get the minimal error in your test data set. I am hoping that I am able to make myself clear. So you need to minimum stop here, so that your stop test error is minimum. So which might not be the minimum for your training error. You might go here, but you need to stop here. So this is the concept of your early stopping in the specifically used in the uh, uh, neural networks. So here you need to stop your training in such a way that you have the minimum test error. So whenever, so you will be doing simultaneously training your model and testing your model, and whenever the error rate reaching the minimum, again it starts increasing error rate, you will stop your training the model there and there. So this is quite important, so for early stopping and to have your minimum stop error. So there both the errors are needs to be calculated, the training errors and the test errors, for understanding the variance and the biasness, and doing a robust way of classification and model. So I'm hopeful that it is clear, right? Okay, so this was one thing. So I'll just reiterate it once for all. So we are looking at the classification and the regression, that is the supervised learnings, and we are trying to classify our data sets, our different omics data sets. And now you will, after classification, you are the getting the errors, type 1, type 2 errors. So what we not going at the confusion matters, but we generally the model shows some error. So gradient descent and the regularization is trying to reduce the cost function, and on the basis of the weights and the sizes and the directionalities. So gradient descent has a problem, is that if it is non-convex problems of the saddle point and the local minimum, whereas your regularization is what it's doing is that it is counting for the weights of the errors. So if you are using ridge regression, it will take the sum of the squares of the weights and would try to produce a new line which helps you to perform the classification. Whereas in the lasso regression, it would be taking the absolute values of the counts. Okay, so after that, when you get the model, so now you, the model won't show always a exact accuracy or a very high accuracy of 80% or 82%. Now if your model is showing 78% accuracy, so now whether you will be taking it forward or not. So now then there is the concept of your precision, specificity and sensitivity. So the precision says that how good is your model predicting at your that out of all the predictions that have been done, how many are correct. That is the true positives divided by true positives plus false negatives. Why false negatives? It's that sorry, true positives divided by true positives plus false positives. Why false positives? Because it has also been predicted as positive, but it is not positive. So how good is predicting whatever has been predicted is true. So that gives you the precision. Now if you go for the sensitivity, so you are saying that how many predictions it is predicting the real yes events. So out of all the yes events, how many real yes events are predicted? That is your true positive divided by true positive plus false negative, because it was positive and has been termed as a negative. Whereas in your specificity, is that how much have been predicted the real no events. The true negative divided by true negative plus false positive, because it was actually negative but has been predicted as a positive. So this is your concept. Now another thing what is there to help the model to so another thing that we had discussed is the minimum to have the minimum test error, so to have an early stopping, especially whenever we perform the epoch in uh, the neural networks and all other kind of things where the chances of data being overfit or underfit becomes very much frequent. So the number of epochs that we need to have, which coincides at this uh, what you call that the intersection where you have the minimum minimum test error, and you will be doing a early stopping. So now another thing that it is being there is the cross validation, which again is very much useful and frequently used in our kind of biological data sets, because this helps us to keep the check in number the models. Because of the sample size, our models generally tend to become overfit, or it does not able to classify accurately. So how it gives you the stopping? So iteration one, there is a test data and there is the training data. So if you iterate different sets, or you take the after k iterations, it becomes all data is covered. So this is the most simplest way of understanding cross validation. So we'll be looking into one to one. So a technique for validating the model efficiency, if you go for the definition, by training it on the subset of input data and testing on previously unseen subset of the input data. So what you are doing is that you have, for example, if you take certain data sets, so now what you will be doing, so you can see that what you are doing is that you have all the data sets. Now you are dividing this into a certain subset of data for training, and whatever unseen data set is there, you are trying to testing it out. So the methods that are used for cross validation generally are: one is your validation set approach. So here what you can do is that you can divide your data sets into 50%, and 150% will be used for training and the other 50% is used for training. So this is a kind of a bias, but if you divide your data sets into 50%, then what will happen is that it might lose out on some of the important features from your particular data sets, and it will not be used. So another is the leave p out cross validation. So among the cross validation, another method can be used as a leave p out cross validation, where p points are taken for training set and p minus n points are taken for validation, and the training set is repeated for each one of the p points. So you will take out p points for your training set. So this training set is repeated for each one of the p points. So this is known as your leave p out cross validation. So where you are taking certain data sets for your validation. Another very important and very popular method for your cross validation that is being used is the leave one out cross validation. So one data set each is taken out for training, and in samples in training data set it will have. So for example, you have 100 data sets, you will take out the data set one, and you will divide the 99 data sets and perform the training test. Then you will include the one number data set, and then you will remove the second data set. In this way you will be doing for each one of those data sets, and you will leave one data set out. So this is known as your leave one out cross validation. Another is your k cross fold validation. So another thing that is being used extensively in our kind of data sets, which divides your input data sets into k groups of samples of equal sizes. So if there are, for example, 50 data sets, and if you do a 5 cross fold validation, so you will divide the data sets into 10 samples. And then prediction uses k minus 1 folds. That is, you will, if there is you are using 5-fold cross validation, so 4 folds will be used for training and one will be used for training, and then it will be iterated again and again. So one fold, the second fold, third fold, it will leave this out, and it will perform the k cross fold validation. So another is the stratified k cross fold validation, where the prediction, so different between your k fold cross validation and the stratified k fold cross validation is that uh, it uses a prediction being used using the k minus one fold, and the rest of the fold is used for your test set. So it is process of rearranging the data, so each fold or group is representative of the complete data set. So among the uh, k minus means the folds, it gets rearrangement is done, so that it's performs a group of the good representative of the complete data set. So there is your k fold cross validation. Another thing is the stratified k fold cross validation. So the most things that we generally used in our kind of your omics data sets, one is your leave one out cross validation. So leave one out cross validation helps very much to understand that how particular data sets and including, and it helps you to keep the models to be in check and not to tend to become overfit, because it helps us to understand that how the model is behaving by including and excluding one data set, each data set. And k-fold cross validation is also being used when it is divided into this sample size and the model is being iterated differently. Then what we get is that the mean AUC, that the mean accuracy for each of those fold data sets, and then we can choose our model accordingly, that which one is behaving the best. So this is another score. So cross validation is another approach that is being used for specifically in the machine learning models. So this is another score, is that F1 score, when you have more than one class or level, and then you calculate the mean of the precision and the recall. So this is known as the F1 score. Another thing is the when you try to put the uh, when you try to plot your true positive rates and the false positive rates. So AUC and ROC probability values so gives you in the between the binary 0 or 1 values. So when your data set is balanced, so the difference between your true positive uh, and the false positive rates, it provides you a better understanding of it. So whenever if you try to do an optimization with the different k cross fold validations, so if you have 10 uh, cross fold validation, so you will have 10 AUC RUC curve, and the mean of those accuracy will tell you that for your particular model. So for example, if you take naive Bayes or SVM model, so what is the mean accuracy after you have performed the 10 cross validation for your particular sample set? So that will provide you the exact accuracy of it, and you can decide on which model to take it forward accordingly. So similarly, the this values helps you to understand that a poor classifier or a random classifier or a good classifier that can predict everything. So this is again important to understand that if we get certain classifier, and it helps us in understanding the classification. So whether is that it's randomly doing or not. So in the whole omics data sets, if I reiterate it once again, so here we are aiming for understanding the classification, but things why we need so many kinds of validation and all those things is that it doesn't have, it should not happen that one molecule or biomolecule that we are reporting or we are saying that are able to segregate one or a set of biomarkers, that is not coming as something which has been done randomly for that particular data set or subset. So that's why it becomes quite important for us to understand that these so that's why in the statistical test we try to do those kind of corrections and those kind of do strictness to understand that it is not randomly distributed, randomly coming as a classifier. Similarly here, So here what we are looking at that they are actually able to classify and are not a random classifier. So this helps us to understand. So now, for instance, I have just tried to certain bring concepts of the models or the different kinds of models that are generally used, like the support vector machines or SVM. So these, like the linear regression, what we were looking at, the simple line which is trying to separate your data points, and then you are trying to find out the errors and trying to find out the best fit. So here in this example, like the support vector machine uses a plane which having your positive hyperplane and your negative hyperplane, and which tries to separate your um, data sets on this plane, which is known as your support vectors. So this I'm not going in detail for each of those algorithms, but these are the major but these are the major that are being used in the data sets, in the biological data sets, which help us to uh, get this kind of uh, classification with a high accuracy. Another thing is the tree-based methods, like the single decision tree or the random forest with the number of ensemble uh, uh, decision trees to classify and split your decision, that classifications into that whether it is belonging to this label class 1 or class 2 or class 3. So these are mostly the things. One is your support vector machines or these things, another is the tree based method, and another one is the naive based, where you attain the Bayesian approximations to classify. So these are different algorithms that take place, and how it is developing an accuracy classification accuracy models, or uh, accurately classifying the things. So now after this, there's another concept is the association or the marker selection. So why this concept is required? So now you can understand that for your, for example, if you are working on a transcriptomic data set, you have 20,000 gene sets, or for a proteomic data sets also 5,000, 6,000 proteins data sets. But when you are trying to build up a model or optimize a model on that, so you can understand that all those proteins or genes are not actually classifying your disease, and or all not at all increased or decreased or differentially expressed in that particular disease condition. Some are noises, some are housekeeping ones, some are not accurately classifying or building the model, just increasing the dimensionality, which is increasing the complexity of your model and increasing the computational time as well as the error calculation and all. So it is increasing. So now what you can do is that you can select a subset of the important features based on a score or correlation function before employing any model. So if you think that just increasing this having this kind of or this many the features in your data sets, and if you try to uh, implement those in your algorithms, then it is increasing your complexity, and it is not coming of any particular help. Then what you can do is that you can select a subset of the important features based on your certain scores or correlation function, and then you can employ any model. So there are certain filters like univariate filters, including like the information gain correlation, or the multivariate filters like your minimum uh, redundancy, maximum uh, accuracy. So what is there is that, so also there are some redundant genes or the proteins which actually means in the same function but is of not use for your particular disease. So you can filter it out and then perform any kind of model based classification. So this is one kind of process where you can, after data pre-processing, you can select or extract out your features and then perform the model construction or validation. So another thing is that the hyperparameter tuning. and the best model versus the model training. So in the model training, after you get the best model parameters, so you need to tune your parameters or the hyperparameters for each data sets. So the most thing likely is that whatever we are trying to do is to get the maximal accuracy of our data sets. So that's why we need to have a best hyperparameters or the best model parameters. So this is another concept that is there for the known as your hyperparameter tuning, so that you can, if you come across these concepts anywhere, you can understand what is uh, there. So this is one kind of thing. So here, this is how the hyperparameters optimization can do, is that the number of layers, number for this is an example of where you can have your uh, specifically for your the deep learning or neural networks, like the number of layers, then learning rate. So you can see that this comes on to all your parameters, and you will be optimizing the weights optimization, and then you are calculating the scores 85%, 80%, 90%. Then you are looking for your markers or hyperparameters that it's working optimally well. So this I wish to give you a case study of how you can select out the features and develop the models which will give you. So this is a paper which came from our lab and is being recently published. So you can see that on the basis of certain scores, a certain set of proteins are being selected, and then the model optimization is followed, done. So as I was mentioning you that how you can do that using the AUC RUC curve, you can try to find out the best models that is being uh, working and taking place. So you can select the best models, and then on the particular those subset of the features, so using the filter method or the filtering strategy, then you can perform the uh, test out the models, and you can get the accuracy scores, the true positives, the true negatives, and the false positives and the false negatives. And then you can calculate your precision recall, and then you can set out that how many that how accurate it is, and how the model, the set of the markers which you can take it forward. So you can if you want, you can go through this as well to understand it more. So this was all about that how accurately we can classify on the specifically on the classification, and how the different algorithms and the models can be taken forward, so that which we can use for our analysis, which for better accurate classification of it. So now there is so we have done some kind of things on uh, a set of things on the for the proteomics analysis on metabo analyst. If we if you can recall other things on the some, we have seen visualize the genomics on the IGV integrated genomics viewer, or we have done seen the Morpheus for which the associations or the genetic things are there. Similarly, we have seen certain uh, on the uh, that is your uh, Morpheus and those things, where we have done the data analysis, and where you can do the data analysis and all. So now, after we have done all those things, so now not only we are looking, we generally tend to look for differential diagnosis or the differential prognosis, but we also look to the set of the genes or the proteins, and also try to understand the biological mechanism, molecular mechanism that is working behind our that particular disease, where you are getting a certain pathways and the networks that are being perturbed for those particular kind of disease. So what actually is happening that the disease is taking place, so that you can design novel drugs, or you can design certain help for the patients. So here, this is one of the things like the Webgestalt, which is a web-based tool which you all can perform, on which you all can perform the analysis. That is a web-based gene set analysis toolkit, which helps you to translate your gene list into biological insights. So before going into that, so here the input, when you provide your input gene sets and using the pathway database. So in the pathway database, it contains a number of list of pathways, so it can give you a functional pathway analysis, that what are the different pathways that are being put up for your particular disease. So you have over representation analysis, so that is your differential expression analysis and the differential expressed genes. So number of, so what exactly does your does it mean over representation analysis? That is the number of DE, that is the differentially expressed genes and the reference genes in each pathway. Okay, so that is meaning is the over representation analysis. Another is the functional class scoring, that the gene level statistics and the gene set, the pathway statistics. Similarly, is the pathway topology or the differential expressed genes, or the so then you will finally assess your pathway significance. So what is over representation analysis? So this is a statistical method. So over representation analysis is a statistical method that determines whether a genes from predefined sets, example those belonging to your specific gene ontology term or a cake pathway, are present more than would be expected in a subset of your data. And what is the difference between a gene set enrichment analysis, also called, which is known as your functional enrichment analysis or pathway enrichment analysis, is the method to identify your classes of genes or proteins that are overrepresented in a large set of genes or proteins and may have an association with your different types. So there's a subtle difference between your overrepresentation analysis and your gene set analysis, gene set enrichment analysis. So it is over representation analysis just give that if it is present in an over expected or over represented in a subset of your data for a certain pathway, whereas the gene set analysis to identify uh, your classes of genes or proteins that are over represented in a large set of genes or proteins or have an association with your different phenotypes. So this is the major difference between over representation analysis and your gene set enrichment analysis, on which we can uh, perform the analysis. So this another important thing is to understand the protein interactions which generally perform and leads you to the, so this is another concept, that if certain proteins are perturbed, that this not only remains individually, but they work in unison, and there's a lot of network as well as work into place for and so this kind of understanding is also important. So this is a functional enrichment web analysis tools. So this is Webgestalt. So let us go into the demo directly. So this is the interface of Webgestalt. So there you can use organisms of your interest. So these many organisms are there. Homo sapiens method of representation. So here, so I have given you the understanding the meaning or the difference between your over representation analysis and the gene set analysis. Over representation analysis will give you that if the number of genes for a particular gene ontology or the cake pathway, if the number of genes belonging to that pathways are very much present, or the number of genes present are extremely high, then it will give you. But in the gene set enrichment analysis, it will that the number of genes or proteins that are present in a large in all the sets of genes belonging to a particular pathways that has some phenotypic association, and then you can choose your uh, you can like where I have used Homo sapiens, where we have given over representation analysis. I have used functional as pathway, or you can use as gene ontology, but I'm giving pathway. Function database you can give as cake, panther, reactome accordingly. Okay, so here you can have like the Illumina or the Affymetrix IDs as well, or you can give the gene IDs. So if I have the gene ID symbol or the Uniprot Swissprot or the gene names. So I'm giving the Uniprot or Swissprot. Now I'm showing if I go here. So now there is a protein IDs, but ideally what should be the workflow? The workflow should be like this, that we are doing it in a metaboanalyst, or in a not in a metaboanalyst but in a secondary classification. So specifically what I had shown in the metaboanalyst or other software that you can use, like the Protege or all those software, where you will be performing the proteomics data analysis. So I recommend you to follow that step. So you will be performing, you will finding out the differential expressed proteins, and then you will be doing the pathway analysis to find the perturbed regions. So here also we can do that step, but here just for demo purpose I'll be showing that I'll take some random proteins and how it is working in this particular uh, Webgestalt. So now I will just enter. So this is no reference type. So now this is the advanced parameters. So you can see that this is the basic parameters where you will be using your organism, method of interest, over representation or gene set enrichment or pathway cake. So minimum number of genes per category. So if you just click on this, hover over this question mark, so you will be giving you that what it requires. The category with a size less than this number will be removed during the analysis based on the number of overlapping genes between the annotated genes and the reference genes list for the word method. Okay, so maximum number of genes for a category, that will be that for a particular category or those things. So how many genes should be there? If it is more than 2001, then it will be removed. So you can understand that if one or two genes gets identified or overlapped on your more than on 5,000 genes pathway, then that makes no sense. So it can adjust it accordingly, 2000 and all huge accordingly. So again is the multiple test adjustment. So if you just know the concept, or I'll just say that the whenever there is a concept of the multiple hypothesis testing, then we need to have a kind of a correction, because the gene sets, it will be testing multiple gene sets, so then it will, the chances of false positive will become high. So again this concept of false positive come here. So that's why this needs to be used. So here the mostly whatever is that the Benjamin Hodgberg correction can be used, and it will be helpful. So if the significance level, again you can use FDR or the top 10. So you can play it and you can check for both the things. So now let us see step 10. Hmm. Yeah. Yeah, so what you can find out from here in the table as well as the bar chart, like the hippo signaling pathway, cell cycle, neurotrophic signaling pathway, viral carcinogenesis, PI3K signaling pathway, etc. to be coming out. So here you can also have a kind of a volcano set. But if we go here and if I give you, sorry, genome coding protein, yeah, here you can see that how much so it will come like different diseases. So this is for the ORA, but again you can, so since we haven't taken any differential genes or differential proteins, I have taken only the random proteins for the this purpose, demo kind of purpose. So that's why the result won't be so much similar with the certain disease pathway and all those things. But you, when you perform it, so you what you do is that you take upon your differentially expressed proteins or the genes and then perform both upregulated and the downregulated or simple upregulated and then try to find out. So that's why you will not uh, uh, get so many things here. Also, sorry, so for the gene set enrichment analysis, what we need to perform give is the expression level as well. So for whenever you are doing the GSES, since so it will require your expression values as well. So let us today keep it till the ORA and overall representation analysis only. So we can discuss this thing in the next week regarding the your gene set enrichment analysis. So I've just taken top any random 50 proteins. And then you can change your parameters accordingly. So you all can try to use this with the different data sets and the different protein IDs. Specifically from the UniProt, you can choose any random proteins and try to play with the parameters to check on that. If you have a your own data set with certain genes, so you can here use, you can easily you can see that these are me Affymetrix and Illumina and Agilent. So if you want to use those kind of data sets, then you can do that and use these gene IDs and try to for any particular disease you can try it out the different pathways what are coming if you have your data set. Otherwise you can also take help of other tools and other things. For instance, in the brain plot, also for different diseases, you have your different disease IDs and the different genes that are upregulated, downregulated. You can use that also as an input, as well as if you have your own data set, you can as your input and can try it with the oral representation analysis that how it is coming. And accordingly, we will discuss in the upcoming week for the gene set expression analysis. Yeah, so if you have any question.